Hey, so in this video I wanted to talk to you about calculus and maybe introduce some of the ideas and some of the important identities that we're going to use. It's going to be very superficial on the surface. We're not going to go in depth into much detail about the importance of the calculus, but at least I hope that this will have this will be useful introduction to what we're going to be doing later on. So anyway, calculus is concerned with differentiation and integration, and this particular part of calculus is going to be looking at the differentiation of functions. So I guess this whole idea of differentiation emerged from this kind of analysis of functions on a plane. So here we have a plane and we have a graph of a function f of x, where a value of f of x is shown on the vertical axis and the arguments x are on the horizontal axis. And just to make sure that we're using the same language, I want to remind you that when I say f of x equals to something number, what I actually mean that there exists some expression, function of x, something like, for instance, 5x squared plus 3, and that expression takes in some number x as its argument. So it takes this number and then it applies this procedure to that number and then returns a value. So the value that's returned from the procedure is the value of the function, and the procedure that's carried out on a given number is the function, and finally the number that goes into the procedure is the argument of the function. Now in this case what we have is arguments of this function are on the horizontal axis, x-axis, and the values of the function are on the vertical axis. In analyzing this function, what we want to find out is by how much is the function going to change if we change argument by some quantity. And the way to look at it is to look at the difference between two arguments, some two arguments, for instance in this case x1 and x2, the difference between those two arguments, and what is the difference between the values of the function for those two arguments. So we have two values of the function. We have two values of the function and two arguments, and then both of those quantities, all those quantities as they're known, are denoted by points A and B. Point A takes in argument x1 and returns value of f of x1, so value of the function at point x1. Point B takes in argument x2 and returns value of the function f at that point x2. Those two ordered pairs are coordinates of point A and B. And what we are concerning ourselves with is the change of the value of the function as we change the arguments. And we can see a couple of examples over here. Our function is a quadratic function, f of x equals to x squared, and we're taking arguments from the horizontal axis. So for x equal to 3, the value of f of x is equal to 9. For x equal to 2, the value of f of x is equal to 4. And finally for x equal to 1, the value of f of x is equal to 1 as well. And you can see that if you go between 1 and 3, the value of the change of the value of the function is quite striking. But if you go between 1 and 2, it's less, and finally if you go between 1 and 1.5, it's less still. And that's an interesting point, that as you make the differences in arguments smaller, the differences in values of the function become smaller as well. And this is something that we're going to be using in order to find out what's known as the derivative. And I'm going to just introduce this here, that derivative is telling us what is the instantaneous rate of change. So what is going to be the change of the function if we change the argument by just little? So how do we arrive at that? Well, what I'm going to think about is how to express the value of that slope between 2 points A and B. Points are on the curve. So the coordinates of point A are given by some argument x and the value of the function y, which is obviously the value of the function for this argument x. And in a similar fashion, I'm going to have a point B, for which I will have argument equal to x plus delta x. Note that if my x is over here, then the value of this argument over here is x plus delta x. And for this argument, for this number, the value of the function is given by that number y plus delta y. So what I want to find out is what are the differences between those two quantities, between value of the function at b and a, and the values of the argument at x and x plus delta x. So obviously the delta y, the difference between the two values of the function, is simply calculated by subtracting f of x plus delta x minus f of x. So that's my number delta y. And then the difference between the two arguments x and x plus delta x is simply delta x. And I can tell that that slope a and b, slope ab, the slope of the segment connecting a and b, is simply f of x plus delta x minus f of x, all that over delta x. Okay, but that doesn't really tell me much about the derivative. What I'm going to do then is I'm going to be making this quantity delta x smaller and smaller, and I'm going to give it name dx, which is going to mean little bit of x, a very, very small amount of x. And we can say that dx tends to 0. So as that quantity dx tends to 0, we're actually arriving at our definition of the derivative. So the derivative of the function f of x is a function or a number, but generally a function, which is obtained when we take difference between a function of argument x plus some small quantity minus the value of the function at argument x, and we divide that difference by that small quantity. And as that small quantity tends to 0, as it gets closer and closer to 0, the value of the returned function is the value of the derivative. So this is a little bit convoluted example. We're going to do this type of procedure. We're going to find a way of determining values of the derivative from this formula, from the first principles as it's known. And we'll see that this is actually, this works. And when it works, it allows us to obtain shortcuts, heuristics, equations that make it possible for us to quickly find out values of the derivatives for commonly visible functions. So for instance, a is a number, is a constant. And derivative of every number is equal to, every constant number is always 0. And if you think about what derivative denotes, derivative denotes change, it kind of makes sense. The constant numbers never change, so their rate of change has to be equal to 0. If we're dealing with a function of a variable that has some power attached to it, the way to find that derivative is simply applying this type of procedure by bringing down the index number and subtracting 1 from the index in the power. Again, we'll do examples of that. Derivatives of trigonometric functions are given here. Derivative of sine of x is cos x, and derivative of cos x is minus sine x. For exponents, we know that their derivative is the same unless there is a coefficient stuck to the variable in the index, and then that coefficient is going to be used in front of the expression. But again, it's quite a unique way of looking at the derivatives. And finally, we have derivative of a natural log. And just kind of maybe as an example, I put in a coefficient in front of variable in the log, and then expanded the natural log into a sum of two logs as we had done before. There should be a bracket over here. And note that the derivative of a natural log of a constant is a derivative of a constant, because this is just a number, so that has to be equal to 0. So then to find the derivative of this, we just need to find the derivative of natural log of x. And if that's the case, that's obviously 1 over x, and we're going to see how useful this is. So that's it for this section, and hopefully it clarifies a little bit for you what's behind the meaning of the derivative, and I hope you find this useful. And in the next video, we're going to move into introduction to some of the methods of differentiation. So thanks for watching.